So welcome everyone for the afternoon session. First talk is by Professor Haruzo Hida from UCLA, and he's going to continue talking about non-vanishing modulo P of values of a modular form at CM points.
Okay. Yesterday, I gave a lot of bad talk. I watched my video, and it's kind of funny, but I forgot to actually say many things. So it is FP bar is fixed. And any similar variety hereafter, it was originally defined over discrete variation in W, but I take mod P reduction. And I work over F. So the black box theorem and so on, the statement is all the time over bold-face F. It's a characteristic P statement. Yeah? Rajan asked me that sort of question, but it is not in the video because he didn't have a microphone. And so I rather like to specify this fact. So what I want to prove today is something like that. I fix a sequence of integers, positive integers, this set, of course, this is infinite, and so it is integers. And for given this n underlined, I define the psi that is depending on this n underlined and one more positive integer, j. J I also take positive integer. Non-vanishing theorem, I explained this number j shows up. And this is just this joint union of I of the point SA in VT to the Q, the set Q of ideas finite set is fixed, and with a reducible component of Shimura variety. And that is the class of A of Ni is in the, I often write Knij, that is kernel of CLNI, the projection to CLJ. Okay, so this is a subset of the Q, and this condition, of course, impose condition on an underline. If you choose randomly this, then this won't be there, as I explained last time. And so all this set is non-empty, I of course suppose. So this is the scene set I'm thinking. And what I want to prove is the density theorem. So this is sort of answer of the question I posed yesterday. That is, if n underlined contains an arithmetic progression, then psi, that is psi nj, j doesn't matter. So of course, this condition tells you that these all ni, so nj is bigger than or equal to j. But if you make j bigger, it's just you lose finitely many points. For this assertion, it doesn't matter actually. And so this psi is Zariski dense. In VQ, as I said, this is over F. Okay, so this is the theorem I want to study. And one remark is that if you take entire n in natural numbers, such that this A is in K0n, and I impose that S A n, so this is n, is in the Q. It's quite, because of polarization calculation, it's just quite easy to show that this is a finite union of finitely many finite union, usually one, but of arithmetic progressions. Distance of two numbers in the arithmetic progression you will see later. And okay, so I do some sort of general theory of irreducible component of infinite ranks. Yeah. That is at the beginning, this underlined n is infinite cardinality. So I just want to do some general theory of irreducible components of a Zariski closure. So I just introduce some notation. So actually, you raise the power to the m, then this will become a principal. And further, it can be something like that for C in for phi. C is a complex conjugation in R. So this such minimal m, for example, you just write this m0, then all m, that is some multiple of something times m0. So for this one is the distance of this C intersected with Q, where psi corresponding to that set. So I would say right here that this arithmetic progression of distance m naught. And there's maybe some j is moving, but I don't too much care. All right. So this I will write it again. So I just erase it. So for general, I just write n to be the unipotent subgroup. U basically in OL completed, or possibly, maybe I'd better say that this is F. And this is, of course, I consider it in GR2 of F. A, P and removed. This acts on similar variety and diagonally acts on SHQ. And you just bring it into, so this goes to GL2 of FL and then go into it. Yeah, so this unipotent element also acts on similar variety. And for a variety, Y over F I write the irreducible D of Y to be the set of irreducible component of Y of dimension D. And IRR Y is just a disjoint union of all D of IRR dy, and IRR plus Y is the disjoint union. I remove zero-dimensional component Y, something like that. And I all the time, for simplicity, I assume the K contains N of OL. So this is, I should perhaps have written as an algebraic group. This is FL. So you replace FL here by OL, integral unipotent element. So this is a general notation. And I already have shown several sort of relations of these points. For example, if I write alpha L to be 1, 0, 0 pi L, pi L is a prime element at L, and then alpha L to the I of A, say N, of level N, X, I forgot. That I explained last time, is X of A, it moves I notch, okay? And this is something new, is that gamma is by logarithm. You need to choose logarithm well, but it is non-canonically sort of isomorphic to OL, right? Therefore, if I write gamma n to be the image of gamma inside CL minus n or CLN, and further, you take gamma n to the L to the I torsion point. Okay, so that is X in gamma n, maybe pi L I X is 0, and maybe 1. This is a multiplicative group. This is the definition of this stuff, is non-canonically isomorphic to OL, O over L or L over L to the I. Or L is the erratic completion. However, you can make this canonical. I leave it this to for you exercise that O over L to the I or L, you pick, represent a set U in OL, and then you move to alpha pi L over that to the U of XRN. Then this guy runs in gamma. This is I forgot. Gamma n L to the I. And this is isomorphism. It means this is independent of, and it has to be bigger than y equal to I, otherwise this doesn't make sense. And so this kind of things you can show quite easily. It's just a linear algebra of you apply unipotent matrix to the given matrix I had, given vector I had for the level structure. And then you compute what appears as a abelian variety. Okay. One more thing is that I pick psi inside M cross intersected R L completed cross. Then you remember that M cross is already embedded inside this GL2 of FA P, right, as a stabilizer of X over R. And then you can therefore apply psi, but you further bring this down to EL2 of you also remove L component. And you consider this inside here. Okay? L component also removed. So that's, this is psi goes to psi L removed. Maybe I wrote too high. Let's see the video afterwards. Then you multiply this psi L removed to X of A, and then you get X of psi A n. I should say this looks like a principal ideal, but at level n, it may not be. Okay? So non-principal. If n is big, it all the time becomes like that. And this multiplication permutes this all the time. And this is the kernel of that. So actually, on this psi, there's the action of M cross intersected R, J, L cross acts on this by permutation. Because RJ things fix the identity here, therefore it permutes the kernel element. And for each piece of this, for each I, this guy is the orbit of this action. So this is the ideal multiplication, it turns out to be. My idea to prove this theorem is that I want to show irreducible component 0 of X. K is empty for any K under some assumptions. So I suppose this is non-empty, but there's an action of group semigroup S that comes from, you see, the distance is m. The distance is m. So L to the m is phi complex conjugate. So this guy, I just write pi. And if m is sufficiently large, 1 pi L to the m, you can assume this is just equal I itself modulo your k, because getting bigger and bigger, it converges to 1, the ratio is, right? So it will be, so maybe I would just say this is inside k. That means the action of this one and that one is the same. And this is the element inside the rational element. So this actually doesn't move the polarization, right? Polarization is an ideal class, strict ideal class. And if you change by multiplication, it acts by determinant, and this is totally positive element. Okay. So this S, that is Rj, Rj completed at L cross intersected M cross X, and also alpha to the positive integer power. If I write alpha to this, therefore acts on psi if n underlined is an arithmetic progression of distance m, right? The action is basically transitive, although it's a semi-group action. It's basically transitive by this fact, and each orbit is just permuted by this guy. And this subgroup is periodically open. Okay, so what I want to say is that if this is non-empty, I can have a point x. Then I just Sx, consider the size of Sx is infinity, right? Because it moves one notch above and all abelian variety corresponding this is non-isomorphic. And so it would be infinity, but this is a finite set if you have an open compact subgroup level, because it is Noetherian. So you get a contradiction, and therefore this has to be empty. And then you shrink K whatever you want, and you get the result. So that's how I prove. So I need to slightly more since you know you have the Q, and inside you have this psi, or maybe C intersected with Q, and this is isomorphic, its image in CK intersected with QK inside VK to the Q, just because XA is isomorphic to XA prime is if and only if plus of A is equal to plus of A prime for the same n, same level n. And basically, I have this XA. I defined the abelian variety yesterday. And I have chosen, so this is level n case. I have chosen the basis 1W2, W2. This is corresponding to XR. And then I multiplied alpha L to the n, and this corresponds to XRN, right? So in this way, this is actually XA, and this is, I should say, AN. A is R fractional idea. Then this is Rn fractional idea. And this is a level structure. This is at L, because I multiplied only this one there. So I just take an L component and multiply this. Outside L, what do you do? Because for A is prime to P, so a hat is some ideal times a hat. A is in MA cross L removed. It's prime to P, prime to L, and P doesn't matter because my similar variety is prime to P, right? Then my outside P is just a 1. This is at L. And outside L, you just multiply 1W2 outside L. And this is the level structure This is the level structure of this guy. And polarization, I basically forget about that because anyway, the same polarization plus is. So in this way, I get a really a point AN. And all A, level N, is actually the class of A is for some capital A of N, right? So that's why out of this data, I have XAN also. Okay, so here's some property of irreducible component. So I have psi, and I take algebraic closure, and I pick an irreducible, or this I perhaps write just X. Okay. Then this is inside B to the Q. Then you go down to the level K. Psi bar K is just an image of X and K, but it is a modulo casings in the K, Q, and this is surjective. This is a irreducible tower of simulability, and you get a sub-tower coming from Zariski closure. All right, under these circumstances, I have, perhaps you already saw this well. Under these circumstances, I claim three properties. It's all basically an exercise. One is just a going up theorem. Because basically shrinking a little bit of K, you can assume that this is Proetal. So therefore, this is unramified. May not be Proetal just by Venkatesh's example. And so number one thing I want to say is that I just pick K, fix K like that, and U closed subgroup. If it is open compact finite index, if it is trivial 1, then you recover V to the Q. So it's kind of U is just a closed subgroup. And by going up theorem for Y in irreducible component of xk, you put it back if V is irreducible component of phi inverse Y. Phi is this. Okay. And the pi inverse Y is, of course, fiber product. This is Y times VKQ of EU Q. If Z in this set is actually, you just pull back, oh, I'm sorry, here. Sorry. I have a irreducible component of xk, but it is a sub-scheme of, anyway, inside what xk is, it is a sub-scheme of here, you pull it back. Then, of course, some variety is in it, but some others not. I forgot all I put U now. It's relative. Is actually contained in XU then Z is irreducible component of XU. So for pullback, this irreducible component behaves well. So this is just a going up theorem applied to minimal ideas. You take a fine open of, and it's pullback. This is a proletar, so it's a affine morphism. I define pi lower star of irreducible of XU to be, this may not be just a reduced image by Z prime running through irreducible. So I'm projecting down now. Then, so define like this. Then the claim is that this contains irreducible xk. So some irreducible component, all irreducible component comes in this way, but there are some redundant guys there. You can look at that Venkatesh example. Okay, so I write twice. This is a going up theorem. This is going up. And the third thing is slightly non-trivial, that we have a unique section of irreducible component of 0 of xk into irreducible component of xu. Of the u projecting down to pi lower star irreducible 0 of xu. Anyway, by number 2, it contains, you project by 1 point by pi, you get a 1 point anyway. So it is 0 is kept. So actually, section is goes to this way. Uniqueness is obvious. Uniqueness follows from psi u is isomorphic to psi k, as I explained, right? Or maybe I should say slightly later. Okay. And this is the first claim. Second claim is that irreducible 0xu is in psi u. U can be k, so this statement is also for k. All irreducible components, 0-dimensional, is kind of obvious, right? Is inside psi. And therefore, by this section is just an injective limit, actually. U prime, it's contained in k and contains u. U prime running. Just combine all and move around U prime. So if you take U to be trivial, it's just an injective limit to all k running, and inside gives you that. That you check it in the Venkatesh's example if you want. All right, so I want to let really this group S acting on this. So this is, I'm claiming, I haven't really said so. And I claim that this action is the action of this guy on this psi. If n is an arithmetic progression, then this psi of distance m, this psi is stable under this action of S, right? And whatever you squeeze, the arithmetic progression bigger and bigger the distance, multiplying m to the m0 times 1, 2, 3, 4. In this way, you can just squeeze a little bit. Okay. So the correspondence action so I just pick beta. I only actually need to, this action of this side is very well defined. It's just ideal action. So this side only I care. So beta to be just alpha to the sum I. And I pick a reducible component like k in the beginning. I do it slightly generally. And k I define. So I want to move by beta this guy to itself. That's what I want to do. And I just, therefore, it's as usual as a correspondence thing. I define YU, this is inside XU, to be the union of Z running through irreducible component D of projection U to the K inverse product of YK, but it is inside XU. If this fullback is in XU, it is in XU irreducible component, right? And this is, if U is open, compact, then it is a finite morphism, dimension doesn't change. And U is small, like 1, it is just an projective limit of eta, so dimension doesn't change. So it is just this size Z, so this is inside XU. Okay, so it's XU. One more thing. I define K beta is a conjugate, beta inverse K beta. And so U beta inverse is inside K, right? U is, I'm sorry. U is defined to be K intersection K beta. And therefore, U beta inverse is in K. And often this part, I just write U prime. Then XU, you have this YU. You just split back your component to above tower in XU. Then you move it by beta. Then you get beta YU. And that is inside XU prime, right? This is non-commutative thing. And then you have a projection by UK. Then you have a XK contains YK because I pull it back and then move it, right? Then you project this down to yk, xk, and here, this is u prime k, right? Because it's different and shows up because non-commutativity, and you have reduced image by beta yu. And I just associate this way, but all right. But this guy is a union of reducible components. So actually this guy is, so I just define beta action of yk to be just a set of pi beta z running through reducible d of d of yu. Because this is a union of such component z. It's a set. Correspondence action may not bring 1 point to 1 point. This is the definition. And actually one can show that this is a irreducible dimension d of xk. So it is actually action like that. And I don't prove this, but I only need the dimension 0 case, and dimension 0 case is easy. So I will do dimension 0 case. So this density theorem, perhaps you get it. So we still have some time. Yeah. Okay. So I assume dimension 0 case. Then the yk is just a 1 point xk in psi k. It is in psi k by number 3 because it's a reducible component, 0 dimensional, and it is in psi. Yeah. U is arbitrary. Inside k can be k. Then out of that, you make yu, right? Yu is what? You pull it back, your point xk, and picking all contained in xu. But psi u is isomorphic to psi k. So you pull back this guy to u that contains in xk, but that also contains in psi u by 3. So it is just again 1 point xu corresponding to psi u. This goes down to that iuk. Okay, so I do this diagram now. So xu, here, yu becomes 1 point, this xu. Okay, absolutely stupid. Then you apply beta. Of course, you get beta x xu, well, originally beta yu, but that is beta xu because yu is just xu. And that is inside xu prime by definition. Then you project down to xk by pi, this one. then you get a beta x k. Right? So it's just a one-point action. And I need to show that this is a irreducible component of xk. I don't know it is a irreducible component of xk something. So you take, I use, because it is anyway contained in some irreducible component, it's 1 point. So it is in some y prime k. And you put it back here, you may assume that this beta xk is actually in one of the components in irreducible pi inverse y prime k. Right? So there exists some irreducible component containing this one. Okay, that's the diagram. Now, what you do is beta is the automorphism of VQ. Therefore, this is not a pullback, but beta inverse is therefore, beta inverse is also automorphism of VQ. I apply, it's not a pullback, I apply this beta inverse. What happens? Element beta inverse. So this is alpha to the minus I actually. Then what happens? I have beta xu inside z prime. This applied beta inverse, I return to xu contains beta inverse z prime. And this is irreducible variety. And it will be contained in some zeta double prime of irreducible component of xu, right? There exists an irreducible component contained. This is not a pullback thing, it's just action. Okay? Then this is I started that is irreducible component. Because I started this irreducible component, it's a single guy, it's not a union of anything. So this is irreducible component of xu. And this is also irreducible component of xu. So it's same. So actually, it is same with beta inverse z prime. And also it is same of z double prime and everything with dimension 0. This means you go down to the bottom. You go down to the bottom. Beta xk is in irreducible 0 xk because you, right? I picked in this way. All right. This is the end of the story. And I already used this up. So this proof of the theorem. Maybe I may need it. Okay, dimension z is z dash, and that is dimension. This is, I should say, dimension z prime is therefore 0, but this is by definition dimension of y prime k. That is beta xk. That's what I'm saying. All right, in this way, this S acts on psi n underlined j if n bar is an arithmetic progression of distance m, that is something integer times m naught. And I can make this something whatever large. And as I said already, that the action of alpha I, the orbit of alpha to the n, so if reducible component 0 of xk is non-empty, then I pick a point xk in irreducible zero-dimensional component of xk, then the alpha to the n xk will be in irreducible component of xk. But this is something already x of a, right? Because number 3 tells you that this guy is actually in psi. Also in psi. Okay. So this action, this n, just it moves n to whatever notch, and therefore it's infinite. One side. On the other hand, xk is a Noetherian. So it implies irreducible component 0 of xk is finite. So by this, it's a contradiction. So it is empty. So every irreducible component of xk is positive dimension. And then you start shrinking k. And to the top, every component is actually having positive dimension. And actually, this S kind of things permute everything. So it's actually equidimensional, positive dimension. And therefore, some component, positive dimensional, contains point of psi. And as I said, that psi is stable under that S. And therefore, by black box theorem, it is Zariski dense. I have still 10 minutes, right? Yeah. Okay, so I might try to prove it's all assertion going up theorem and so on is fairly stupid, but let's try to say property 3 is kind of slightly intricate. So I try to prove property 3. So squeezing a little bit, I can assume that UQ, this KQ is pro-eta. So it is an affine morphism. Well, therefore, its closed subscheme XU goes to XK. This is still affine, no, may not be at all. So that means can assume you cover this by spectrum of affine algebra and put it back, that is still spectrum of affine algebra. So you can assume VUQ is spectrum of A prime, may not be Noetherian dependent on U. VKQ is spectrum of A. But I can assume U to be once for finite extension, you can prove it, then you take an injective limit and you get everything. So therefore, I can suppose that U is open compact. Okay. So that means finite index, and it's a finite morphism. It's all finite. Then the XU is therefore spectrum of B prime, and the XK is spectrum of B, and B prime is just A prime modulo intersection of all prime inside this psi U of P, and B is A modulo the same because you intersect it, it's the projection, P intersects A. Okay? That you have. So pick M maximal ideal of irreducible zero-dimensional B, spectrum B. So this is actually maximal ideal and minimal ideal. Because it is irreducible, it is minimal, but zero-dimensional, it is maximal. And max. Intersected A. No, because it is psi U and you project down. That's like taking intersection. And that's same as K. For this guy is the element in XIK. Okay. So this implies B is B. So this means M is actually in the connected component of spectrum of B, right? Other minimal ideal outside M, you add it, then this is maximal entire thing. So that means B some complement direct sum B over M. And this is contained in B prime. And you apply the idempotent of this guy, you split this guy in the same way. And this is a dimension zero thing because B to B, B prime to B is a finite morphism. Finite. Yeah? Because I assume that is open compact, and this is enough. Then this is a product of field because it is in a Noetherian case. Field is just F, it's algebraically closed. Therefore, this implies the connected component of B prime of MB prime projects down to connected component of spectrum of B over M. This is a single point M I started because this contained in there diagonally. Therefore, by lower star, irreducible zero B prime contains irreducible zero. M is arbitrary, anything comes from above. So that is B. Some M may not come from that because I pick something inside the irreducible component. So if M is not in Xi k, then it is not in Xi k means Xi k has to be in spectrum of Bm, right? This guy is not in Xi k, so it will be there. But that's impossible. This is a Zariski closure of entire Xk. This is impossible because Xi k bar is spectrum of B, entire thing. So it's a contradiction. This tells you that M is in Xi k. That's what I wanted to show. And then the pi lower star irreducible 0 of xu projects down to irreducible 0 of x, no, image pi star irreducible 0 of xk, and inside I have irreducible 0 of x u, I'm sorry, xk. And I have psi u is isomorphic to psi k by projection pi. So you have a section, unique section S, inverse of this map. And then all this statement is almost obvious, I think. I have exactly on time, I think, and I stop it.
So let's thank Professor Hida. Any more questions or comments? I guess there are no questions, so let's thank Professor Hida again.